To have a webinar about the architecture of data lakes. My name is Yannick. I work for Computer Futures as a recruiter with everything focused on data and BI, going from data engineers to artificial intelligence, machine learning, stuff like that. Now, the reason why we're going to do this is that most of you will know recruiters mainly as the people with annoying phone calls, the emails, with irrelevant resumes, but we're trying to do something different at Computer Futures and work with a strong community. A few years ago, some people of you might know Levi as well, we started our own webinar and meetup sessions. Now, we noticed that as recruiters, we talk to a lot of interesting people, going from managers that work in new technologies at startups, larger companies, and they develop cool products. Same goes for the engineers, for the data scientists. But that knowledge that often stays with the people, and we want to see if there's a possibility, to give those people a platform to talk about their passion and about the interesting facts and things that they do. In this case, it is Thomas. And this way, everyone in the community that we're trying to build can learn from each other. And I think especially in the whole data domain, which is rather upcoming and new in Belgium, it comes as a blessing. But I don't think you're here to talk, to let me talk about Computer Futures and a sales pitch. So I'll give the word to Thomas, who will start with the webinar. Maybe one last point as well is that with the questions, I would ask everyone to write down their questions in the chat box. The webinar is separated in chapters. After each chapter, we'll have a quick Q&A, see if there are a lot of questions. If not, then we will continue the webinar. Is that good? All right, Thomas, that's the word goes to you.
All right, thank you. So, hello everyone. My name is Thomas. I'm a data engineer and architect for InfoFarm. We at InfoFarm, we have like 3 big pillars where we focus on. One is data science, so applied machine learning. The second pillar is big data, of course. And for the third, we do training and workshops and, of course, webinars like we're doing one today. But again, this is not about InfoFarm or Computer Futures. We are here to talk about data lakes. So maybe to sum the entire webinar up, this is an introduction to data lakes, like basic concepts, basic strategies to handle certain things, and at the end, I'm going to share some challenges I faced the past years, so you might not follow the same sinkholes that I did. And so we're going to start with some basic concepts. There are a lot of terminology used around the components of data lakes and all that, and a lot of definitions. I use the terminology I picked up at one of the clients I worked at. I really like those. I still use them. But again, you'll see that these are not set in stone, but the basic concepts behind them are. Then we'll take a look at the building blocks. So we have those concepts. Now, how and what do we need to do to realize and deploy those concepts? Then I'm going to show some use cases. This is mainly just to have like a practical approach to the stuff I discussed before. So it's a bit more sensical, at least for me it is. I hope it will also be for you after that one. And then at the end, I will talk about the challenges and the sinkholes and some stuff to think about, like I said earlier. So the concepts. Well, of course, we begin with the data lake. I pasted here a quote from the CTO of Pentaho. I like this one very much because it compares it to a data warehouse. And it uses, and I will keep using this metaphor of water lake, all that stuff throughout all the concepts. So if you think like a data warehouse is a store where you have bottled water, where you can just come in and buy clearly structured, packaged water for a clear purpose, that's a data warehouse, where a data lake is more like the name says itself, the actual body of water that is available. So it's the more data in a more natural state, and you can use it for multiple use cases and multiple scenarios that you want to that you have in mind. Now, when you're a big company, it's possible that you have multiple data lakes, that you have to have some kind of structure between them. You can see a data lake, you can base it on, let's say, a data source as a category. For example, you can have a data lake where you have everything from a data warehouse, or you have everything from a certain website. But you can also do it based on a category. Let's say we have a data lake of users, so everything related to data of a user, of a client that we have will reside there. The reason why we do this is the second point, to have a single truth. So when you have a use case and someone from business says, well, we want to have this information in a dashboard, how can we gather this information? It's important to know that, well, information for a user, it's available right there and only there. There is no different version. There's not like, okay, we have a version with those columns there. We have a version that resides on another data lake that has a combination of some filter. You have one truth. You want to know you have users data. I can find it right here. So in the user data lake, for example. Data lake is an abstract concept, so it can have multiple storage types. It could be that your data, you have some user data that's on a Kafka topic, you have some user data that's in Parquet files on a file system. So that's just the abstraction above it. And it's accessible for multiple users. So it's not made for one use case or one consumer. It's made so it's actually your starting point for any data-related project that you want to build. So this is the highest level, the data lake. The other concept that they used was Puddles. So you have the big data lake, and then you have the smaller Puddles. A Puddle has one schema. So let's say we have a data lake of users, and we have some billing information. Let's say, so that's a Puddle billing information that has a certain schema. And we also have information of transactions they did, like stuff they bought or stuff they used or they clicked on, and that will have a different schema. So that's a different Puddle. So you can see that the Puddle in a data lake is more like a consistent state of the data that can be used. And the important thing is that the data that it's queryable, it's actually that it's usable. You will see that there are different types of Puddles, and I will discuss them now. So we start with the raw Puddles. So when we ingest data from sources, if you ingest it from like a database or some structured store, then it's mostly good data, and there are some rules there, so it's normalized. So probably it's going to be fine. But a lot of the time, especially when you start to look at IoT stuff, you will have really, really crappy data, and you're not certain. You cannot vouch for it that it has this schema, that this field is available. So it's not ready for use. So we call this the raw data, or the red layer, someone else called it. But this is just a straight dump from the source system into the data lake. Now we do this because, let's say we do, we start processing the data, we clean it, we set it somewhere, and then after a year we say, well, actually we want to do it in a different way. Then we have to go back to the source system and ask for, okay, can you give me the data from all the data from last year? And they might say, well, we don't have it. We only have the last month. So it's just to not be dependable on your source system, and also just don't. So for avoiding some load on that source system, if it's a not big data tool and you're going to approach it in a big data environment, a lot of those are going to be very unhappy database admins when there's so much load on it. So now we have ingested our data from our source. it's very dirty. We don't know if we can use it. It's muddy. The next step is, of course, accepted puddles. So this is a cleansed version of those raw data. What do we mean with cleaning? We apply a schema on it so that everyone that is going to use this data, we can ensure them, well, it has this schema. So it has this field, it will be this data type, and well, it might be optional, the field, it might be zero, null or not. So that's one side of it. The other side of it is normalizing, especially when you're in next steps, you're going to join the data and use it together. It's good to have like one format of dates, for example, or that you say, well, when we store an address, we will do it this way. So like one big string, or we will store the street and the house number separately, stuff like that. It's hard to do it when you already have the data and you have to do it retroactively because you have so many data, so many formats, and you have to change a lot of it. It's actually, if you're going to start doing it, it's good that you define those rules at the beginning. If you don't have it, well, fine. It's not a blocker. You can still in your code where you're going to join the data, you can still do those transformations, but you want to avoid doing the same thing over and over and over again. That's why if you can do it in the clean, in this step between the raw and the accepted, it's way better. Another thing to keep in mind is time sorting event data. We'll discuss event data a bit further, but basically it's about transactional data. So data that happens in a point in time, and we might ingest it at a certain date, but it might be data from another date, and which is way more relevant. Let's say we have a user and they want to use stuff a user bought, and they want information from a certain month. We want to just load that month and not have to look in our entire data lake to see, okay, but the event date, which is now exactly the month we need. This will become more clear. I will discuss this separately, but just so you know that this is also where it happens. And it's ready for any use. As you can see, just one big body of water. Anything that wants to do something water related can use this for any kind of use case you can imagine. So this is the baseline of the data lake. So this is just data from one source, not enriched, not aggregated, not joined, just cleansed and ready to be used. Now we want to do some cool stuff with the data, and well, most of the time you're going to aggregate it and join it, enrich it with other types of data. So now we come at the master puddles. So this is the next step, and these are like single use case projects, like businesses. We want to know how much a user bought a certain item at a certain point of day. This is very, very specific, and you might have to use different accepted puddles, so different data sources that we have in our data lake to achieve the goal of this certain puddle. Yeah, most of the use cases will be around reporting or dashboarding or creating aggregates or defining features to export to a data warehouse or something. So in the beginning, we had a big muddy puddle where we are not sure what we could do with the data, and well, we wouldn't really want to give it to our developers to work with. Then we have our accepted layer where we have a big body of water that could be used for anything. And now in the end, we have a master puddle where we use that water to build a kiddie pool, a certain use case, for example. Now we have our different puddles of stationary stagnant data. Now, of course, we have to flow the data from ingestion into the raw puddles, into the accepted puddles, into the master puddles. And this we call streams, because again, it's with the water metaphor. And while we have streams of ingestion and processing and exporting the data, as you can see. I'll give a clear example to just tie it all together. Let's say we work at a telecom company and we want to send, we have a special package for people who want to watch the football games, the soccer games. You have to pay extra for it, so we want to target some some users of us, some clients of us that are interested in sports, but have not yet bought our package. So what do we need? Well, of course, we need to know what our clients has been watching on TV, and we get that information from the box. We have that information on what the user is doing on the TV. And also, of course, because we're a telecom company, we have an overview of what is on TV. With these two data sources, we can determine what a person was watching, and therefore we can decide which person is watching a lot of sports and could benefit from our package. Let's say the TV catalog data of what is on TV is in a database, and we just take a daily snapshot of it because it will not change that often. It might change a little bit, like this show will be a few minutes earlier or a few minutes later, but it will not change that often. That's why a daily snapshot is fine. And those clicks or events we get from the box, well, it will be streaming, it will be real time, it will be a lot of data, and it will be dirty data. So because I said the catalog data is coming from a database, it's pretty structured. We don't really need to do a cleaning step unless we need to apply some normalizations on like date formats. Like I said, if you want to do those, I didn't add it in this overview, just because, well, if you're coming from already a structured data source, you don't have to include the step just to include it. Now, on the other end, the clicks we get from the setup box, that's going to be very dirty data, and we need to clean those. So, for example, the timestamps you see here. So at the raw, yeah, you see this is an older presentation. It's from 2019. So let's say the 7th of April, we ingested some data, and it looks like this. So we have a customer. It has a timestamp in milliseconds. It has a channel, and it has what he did. So he started watching at 3 a.m. Then he did a click, and he went to 1. So we could say, okay, he changed the channel. Then he set it on pause. Then he resumed it, and then he turned off the TV. And then we have some record where we don't know what the customer was. Something went wrong. So this is dirty data. Also, yeah, this format, if you do it, if you're going to just chuck it into a dashboard like this, nobody's going to be able to read it. So we'll do some cleansing and some time sorting. So this is the thing I talked about. So it could be possible that there are records arriving from a different date that are not from today. So after our cleansing step, we noticed that there is some data from the 1st of April that came in that day, and we cleanse it with, well, we changed the milliseconds to an actual readable date and time, and the rest we kept the same. We also filtered out the null value because if we cannot tie it to a customer, it's, well, not really data that we can use, so we don't want it. And the rest of the data was from the 7th of April, so that's fine. There we do the same cleansing step. Now, the format that you see here is assuming that we are going to store this on a file system. And on a file system, we want to do some partitioning. This has some benefits. First of all, it's easier to, when you're loading new data, to append to your Puddle because, well, it's structured on when you ingested the data. And when you cleanse the data, well, it's easy now to say, I want all the data from the 7th of April. We can just go to this directory and load I hope you guys can see my mouse, actually. I don't know if it's so. Can you see the pointer of my mouse?
Yes, we can.
Okay, thank you very much. So it's pretty easy to load in this data. If we wouldn't do this, if we wouldn't time sort and we want data of the 7th of April, we have to read in everything of the raw folder and then have to try to filter out the records that we want. Most of the big data tooling and stores and query layers can use this partitioning to only load in this part of the data and not having to go over the entire thing. So that's why we do it. So now we have a cleansed state of our data. We know now we can easily load in data from a specific date. We have data where we are certain that we can link it to a customer because our customer is not null. And we have a normalized version of our date format. So now we have our clicks from a customer. So the stuff we did on this setup box, and we have a catalog of the TV. Now we can combine these two to determine. Okay, so we know that customer 1 viewed VTM from this time, and then viewed a channel from this timestamp to this timestamp, and we can cross-reference it with the catalog, so we know, okay, he watched Family first, and then afterwards he watched Sport Weekend on AIM, and this is important for our use case. So this is the master. This is important because now we can tell, okay, this customer is watching Sport Weekend. If we check some other data from like previous months, and it will keep coming back Sport Weekend, we might think, okay, this guy might be interested in our sport package. So we'll send a trigger to the system that sends a mail to, hey, check out our not so expensive sport package, buy it, you will like it. So this is the concepts tied together with a practical example. Are there any questions about the concepts themselves? So like the data lake and the puddles and the streams between the puddles, is that clear? If that's not, if it's not, then you can ping something in the chat maybe, and before we move on, because well, the rest will build on top of this, so it's important that you guys. I'm gonna try and get the chat here. Okay, I don't see any questions. If there are questions at the end, we will leave some room to also for questions. So if something comes up, you can still ask it then.
Can I ask verbally, or I just need to write it?
Sorry?
Can I just ask, or
sure,
I need to write it? Ah, yeah. Well, if basically let's say the end data puddle, or basically the fully extracted, transformed data per purpose, let's call it like that. The destination is a database. So this basically creates a lot of duplication of data. Yes, when you are on a data lake that is like file-based, I totally agree. That's the way to do it. But if basically the end game or the end destination is also a database or an application or something that is, let's say, structured data, and it's not like, let's say, some kind of another data lake that is used just by certain people, and again, they need to kind of shuffle it. So we can...
Why would you think that you have a lot of duplicate data if it's stored in a database, or that it's going to be exporting to a database?
No, yes, if it's going to be exported into a database, we can basically, let's say, have less puddles. That's what I mean. Like you know, you can start. We could start with let's say the raw data and transform it in one shot into something that is structured.
Yeah, you can, but then the issue there is, if you want to do it, you can skip the accepted step, but it's not very wise to do. But let's say you have a use case that wants to use that data. You have like a complete use case. You want an aggregate on something, and you start from the raw data. You do the entire ETL stuff. You clean it, you normalize it, because you need to filter out some values that are not fine because it's raw data. And then you create your aggregate, and you store it in whatever, a database or it doesn't matter. A puddle could be anything, a database or a file. And now a second use case comes, and they want to use the same data. Again, you have to go clean the raw data, and you do everything you need to do because it will also use that data. That is why we have that accepted layer in between. to have a baseline and say, this is data where you don't have to do cleaning or a lot of ATL on it. You can use it. As it is, because otherwise you're going to put a lot of effort onto your developers that they have to do every time. So
but you can also have the semi-structured data also in a database as well. Today, if Oracle ADB basically gives you the ability.
Sure.
So then you have the staging, not in a file system, but more of a kind of a database. So then it can be like queried. You don't lose the query ability when you have like many stages, which are kind of file system semi-structured data, like the raw is raw, but then you have like another stage and another stage to kind of just like do those, as you said.
This is just a general approach. So a Puddle could be in a database, or it could be a Kafka, or it could be a file system. This is just general. Like I said, if you have structured data in databases, there are some things you don't have to do. You have to be a bit pragmatic about it. But this is just a general approach. I would say that, the accepted layer that you have, I would always have that. Even if it's a database or whatever it is stored, you just want the data ready to use, ready to be explored, ready to be handled in a certain place. And not, you don't want to start from your raw data every time.
Yes, agree. Understand.
Okay, good, no problem. Okay, so now we get into the building blocks. We have those concepts now. What do we have to do to achieve those? Again, these are going to be pretty general because, I only have a certain amount of time to talk about this. Every specific concept and every specific approach to this could be a webinar on itself. So I have to keep it general here. If there are like very specific questions, at the end I will leave my contact information. Feel free to send me an email to run something past me or something. There are many ways to approach these kind of things, and some ways are better than the other, but there are a lot of options for that. So building blocks. First thing is to getting our data, and we'll start with event data. We already talked about this. So this is transactional data. Let's say a user bought something, or user clicked on something. This is data that happened in a point in time. It might be out of order, like the time we ingest it might not be the time that the data actually happened. That's why we time sorted it. So we partition it on the event date and not on the ingested date. And you can stream this or batch this. I just listed some technologies I've used for this. So you can use an Apache NiFi. You can use a Spark to load this data. You can use Kafka. There are many others. Again, I use the same example here just to keep it in context. So let's say we get the click events from a Kafka, but we don't really need this data real time. So we will use a Kafka Connect to write batches of data to a file system on a file system in the data lake. So then we have entity data. It's another type of data. This is like the TV catalog we talked about. This is like a lookup table. This is like a reference. This is not a data with a point in time, although you could make the case that a TV commercial is a point in time, but that point in time might be in the future, let's say with the catalog. So this is not exactly like it happened that day. That's why we approach the entity data. It's you would be inclined to move everything from a certain source to your data lake. But if it's only rarely used or only used like once to look something up, and it is possible to approach it, the source itself, you don't have to always copy it over to your data lake if you just just for the sake of it. So keep that in mind. You might it might be better to do copy it to your data lake, so to reduce the load on the source. And an example of this is that you keep a snapshot every day, so you have a history of a certain state of a database table. For in this case, the daily snapshot. Yeah, I also listed some technologies. There are so many. I'm not going to go over all of them. Let's say in this case, we use Scoop to take a database export from a certain table that contains all the TV shows that will happen in the near future. So now that we have our data, so it could be entity data or event data, how are we going to store this data? We want to keep a puddle in one certain stack. So not like, oh, there's a piece of the user transaction data on Kafka, a piece of it is in S3, we just want one. But in a data lake, we can use multiple sources, of course. We want to use the best, we want to use the right tool for the job. If we have like a small table, we don't have to use a file system for it, let's just save it in a database. But there are three big kinds of storage we can use. So we can use a file system where we can write Parquet files, Avro files, or CSV. Please don't use CSV. I think most of the use cases could be handled by Parquet or an Avro format. This is of course not as performant as a data store, and it also needs some work to be able to be queried. So we need a query layer on top of it before we can query it. This is mostly for when you want to write it once. So it's also very difficult to do updates or deletes on a record level on files, unless you're using something like Datalake. But that's why this is more like data that's not going to change. Then we have a data store, so this could be column or row based. Of course, your file format from the file system could also be column or row based. This is more, yeah, it's easier to approach this data because most of the time it's already provides you with a REST API or a Thrift server or JDBC connection you can make to it. And most of them also provide you a way to update records and delete records. So if you like data, like I said before, that like the TV guide, let's say for now we say that next month Temptation Island will be at 8 o'clock, but actually it's 8:05 the next week. So it might change, and it's easier if you have it in a store than we have it on a file system. And then again, we also have the streaming. So you have Kafka topics where you can store data. Keep in mind that most of the time you have retention time here, so you don't have the data for a long time. You can handle it with like a lot of compacted topics on Kafka, but this is a bit too in-depth to handle here. But keep in mind that keeping your data on Kafka is could be a valid case, and it could be useful. So in this case, like I said, the TV catalog guide, it's not that big of data, it's just a snapshot. And it's, well, it might change on a record level, and we don't really need history of it because, well, the latest version is the version we want. That's why we're just going to save it in a Postgres database. I mean, we don't need to use big data tooling if it's, well, if it's not needed. I think I forgot to remove the Hadoop RDBs. Oh, that might be from the raw. Let's say we put in raw and then in the Postgres, but let's just keep it. It's in the Postgres. And like I said, from the clicks from the setup box, we had a Kafka connected, read it from Kafka topic, and put it in batches in a file on our, let's say, an Hadoop RDBs on our file system. Now, processing the data. So now we have the data. Now we want to do the cleaning and the enrichment and the aggregate step of it. We can do it in batch. There we say, well, we have a frequency that we run it every hour, and we run for the data that we have there. I have it, you run it on all the data because, well, with streaming, you have a certain window of state that you can collect, but here you run it on all the data of that new batch of data that you're running it from. Something you MapReduce, if people still use it, I hope not. You can do it in Spark. If it's small data, you can just do a Python script that does it, or other processing tools. Even just you can, if you ingest your data in NiFi, you can also do some ETL in NiFi itself, for example. Then streaming. I hear a lot of like streaming is a very hot topic. Everyone wants to stream their data, and but most of the time when you just dig down in the use case, do you actually need it real time? Most of the time it's no. It's not that big of an most of the time it's not that big of an advantage to have it real time. Let's say business say, but we want to know real time what is happening, and they only check the report once a day. So why do you have it real time, for example? I would say when you start going into, well, we want it every 15 minutes, well, then you can better just stream it, because especially when you use Spark, you have a lot of overhead around it. If it's 15 minutes, just do it in streaming. I listed some technology stacks for these, but again, there are many others. For this example, I use Spark. I use Spark because, well, the bottom track, the clicks we get is a lot of data, really a lot of data. That's why we want to use, we want to distribute it when we process it. And although we have one of our sources, it's just a PostgreSQL database. So what we will do in this case specifically is we will reading the data from the clicks. We will distribute it over nodes, and then we will reading the PostgreSQL table, and we will broadcast so that every node has a copy of it available of that lookup table, and then we easily can process it without a lot of shuffle and write it to our master Puddle. That could be anything again. And then at the end, we can export the data. So let's say we build some aggregates, or we build some features, and we calculate some KPIs. You can show it in a click dashboard. You can put it again on a Kafka topic. You can do anything with it, just as it leaves your environment. Another tool. So now we have our data is stored. We have a way of processing our data, but we want to do it automatically, and we want to do it in a smart way. And then comes the scheduling of our jobs. So, well, of course, the frequency, you need to determine for each job how frequent it's going to run. Do we want to run it hourly? Do we want to run it every day? Do we want to run it based on a trigger, maybe? And then, of course, the dependencies. When you have puddles, where streams are actually creating dependencies between these puddles, it's important to know that, okay, I can, if I depend on two puddles, I need to be sure that they're both up to date for a specific time that I'm running it. Else I cannot run this job successfully. And also, well, if you're scheduling it, most of the time you have a good view on execution time. So when will it run at what time? If you schedule all your jobs to run at 12 o'clock at night, you will have a lot of trouble, because all your jobs and your cluster will have a massive load at that point. So try to keep a good overview of when your jobs are scheduled to keep a steady load and not a big spike. Yeah, this is just an example from the same example I used throughout the entire tier. So let's say we, from the ClickStream setup box, we want to take a dump from Kafka Connect every hour of the data. And when we have the data from 1 o'clock, we want to process that data at 2 o'clock, because then we're certain that we have all the data from 1 o'clock. So then we clean it, for example. The snapshot of the TV catalog, it's fine that it's daily. Let's just run it at 5 a.m. because most of the people will not work at the time. I hope not. And then when we have step 2 and 3, well, 2 is we could make a case that, well, to create a master sessions, if it's the TV catalog from yesterday, it will still be okay. So it's not like a soft dependency and not a hard dependency. It's not blocking. You can go very deep in this. You can say, okay, for this job, it's fine that we miss 4 days of catalog updates. Then you can still run. If it's more than 4 days, we will make sure that you don't run. For example, you can go very far in this. This is just a basic example. And well, when we have runner master job, we can start exporting it after that one. So it's just, but there are very, very many scenarios and rules and conditions you can create in this. Most of it will depend on the tool that you're using. So now we know when our jobs need to run and on what jobs they depend. Another thing we need to know is, well, what data do we need to run during this run? So for example, let's say we have a job that has been failing. It should be running daily, but for example, here we see your job that should run daily, but it hasn't run since the 7th of April. A developer has found a bug. It was a dirty code that he fixed, and now the job runs fine. And when the next time the job is scheduled, it should run all the data from the 7th of April until, well, the data that it has available right now. So if you, most of the time you keep it in a database with like the timestamp of, okay, this has run on this day. Now there are 2 ways of interpreting this checkpoint. So one of it is, let's say, we start running our job, and the first thing our job does is check in the checkpoint table to see, okay, when was the last time I ran, and it will be a certain point in time, and then he can detect if it's a file system or any other storage. He can see, okay, what data changed, so what partitions of data changed from that point that I have in my checkpoint up until now. So you can say, okay, so I run now. That case, that daytime in your checkpoint means this is the last time I run. I have all changes from when I started running up until that point in time. I have all the changes, but it doesn't tell you I have data of a certain day, because, well, it can say, well, I ran today, but there was no data today. But it will still say, well, I ran today, so I put all the changes. So you have another strategy to use this, and this is where you say, I have ran for the 5th of April. So there is data for the 5th of April. If there's no data for the 5th of April, it will keep stuck on that checkpoint up until he found data for the 5th of April and could process it. As you can see, this approach is good for like entity data or like snapshot data. But if you have time sorted data, like we discussed, you will have data across multiple partitions, and then the first approach is a lot better. Now you can always, I mean, the first one is more of a catch-all. So if you're not certain, it's always good to just say, okay, just see what changed from the last time I tried to run and handle everything that has been added or modified since then. I think that's the best approach in my mind. Then a big discussion, if you want to go in, do you want the data lake in the cloud or do you want on-premise? There are pros and cons on both of them. There are even differences, not that many differences between cloud providers and even premise providers. I think the biggest change, the biggest differences is that if your data lake in the cloud, you have elastic computing and storage. So you're not confined by the hard limits of your hardware. You can always keep infinitely scaling. You don't need that many admins because most of the most of that stuff is handled by Amazon, especially if you use the managed services. So you need a smaller admin team to keep the environment up and running. Yeah, cheaper, not always. Sometimes it is based on use case. So it's one of the points they make that it's cheaper in the cloud, but I always use the parentheses because it's not always. And it's more flexible. Let's say if you want to try something out, it's very easy to just spin up a new AWS service that you want to use, or just yeah, try different instance types, so like more GPU based instead of CPU based. It's very easy to do that in the cloud. It's more difficult on premise. There is a case on premise that they say, well, it's more secure. I always kind of challenge that with, well, if I think the people that handle the security for cloud providers are like the best of the world. So if you're certain that your security team of 3-4 people are doing a better job than them, I'm not always certain, but especially for like banks and other who have some sensitive data, this is most of the times a no-go because yeah, they don't find it as secure. Now you can always do both, a combination, a hybrid solution. You could use your on-premise for your non-elastic load. So let's say we have monitored the load in our cluster, and we see that we always use 30% of our cluster, and then we have some spikes in the day that we go up to 80 or 90%. So you could say, okay, that load that always runs the same, like an hourly job that always has like the same amount of data roughly, we can run those loads on our on-premise cluster, because there we don't benefit from the flexible and the dynamic scaling. And also the loads that handle the sensitive data that most of the business people are afraid of to be running in the cloud. You can run that on your on-premise cluster, and you can use the cloud for your spikes, and to use that as a kind of a test environment, a sandbox environment, or just some ad hoc data manipulation, or just a sandbox of it. I think especially when you use stuff like Kubernetes, it's very easy to implement this hybrid kind of process environments where it will seem as a user of a developer of it that it's one environment, while it's actually an on-premise extended with a dynamical scaling cloud solution. Are there any specific questions on these? I know it's a lot of information, and maybe not all of it is super clear. So that's why if you have something like this is not clear, could you go over that again? This is the time to ask. If not, you can wait until the end and ask the question then. Maybe it will become more clear after the use cases. No? Okay. I'm going to assume. Wait, let me check the chat before I. No, okay. So we will build upon the example we already have for this use case. So we know now what are a certain user or a certain client of us is watching. Now we want to send personal advertisements. So we want him to know how much chance there is that a certain client of us will watch a certain commercial. Because we have this behavior of watching TV, we can roughly estimate, well, if we watched VTM every day at 6 o'clock, the chance that he's going to watch VTM the next week at 6 o'clock is pretty big. So if you want to target that specific user with a personal advertisement, we should do it at that point, because then we are certain we target that user. The eventual application that will be using this data will be a Java application. So we need to be certain that it's approachable via gBC, for example, or via REST. And this is more like, okay, the master data that we have. how are we going to store it? So to show like the thought process behind it. The chance that a certain user is going to watch at a certain time in the future, it's going to be updatable, because every time we get new information, new viewing behavior of this data of this user, it will change. It might affect chance that this user will watch it. So we want the data store, so we're able to update it on a record-based level. Then it's going to be a lot of data, and it will be a Java application with a front end. So we want to have not as much latency as we can get. So we don't want HBase, it's more like a query layer on top of HDFS. I use Kudu now for this example, because, well, at the time we were using a Cloudera cluster, and this is a Cloudera data store. Other stuff that you could use, like a Presto maybe, or another big data store that you have. And now, well, we have it in Kudu, our data, and how do we want to approach this data? Well, you can approach it via Spark, or you can use Impala, and this is the one we're going to pick, because Impala will make it so that we can use a gDPC connection via Impala to query these Kudu tables. So now we have a big data store that is queryable from a non-big data environment, and the store is able to handle updates. I'm really a big fan of Kudu, by the way. If you're ever trying to doubt if you should use it or check it out, definitely do it. Again, it's Cloudera specific, so it's not for everyone. So it will look kind of like this. Now, this is just to show you that the examples that I've been giving are very basic and very, yeah, it's easy to apply it on the concept that I was bringing, because it's very straightforward, like a raw puddle, accepted puddle, master puddle, exporting it. So now just took an example flow from AWS. It's their predictive autoscaling, just to show you guys that even here you can apply these basic concepts of, well, you have your puddles here. So this is data. This is going to be system data of your different AWS monitoring, and this might be logs, and we can ingest those and put them in our raw bucket. We can or in an accepted bucket, and then we have a master project that checks these statistics, and based on that they can send a trigger to adjust scaling. So this is a specific purpose. So this is a master project. Here we just have our data of, okay, these are monitoring from our services. These are logs from our services. This is generally used. And then here in this Lambda function, for example, we define a master project where we have the purpose. Okay, now based on this data, we want to decide if we want to start adding more nodes to the cluster, because we're reaching a critical point. And then again, you can export these via Amazon Athena for this example, to show it in a dashboard. So again, this is not as black and white example as I've been giving to the entire webinar, but still the same concepts can be used. Just keep in mind that you have streams of data between your stagnant puddles. And just keep in mind that when you ingest data, that data is very valuable, not only for the project or the use case that you're working on right now, but also in the future. Your data lake should be your one-stop shop for data for many different use cases. That's why keep it in a natural format somewhere, and then build on top of it for your specific use cases. I think questions about these use cases, these are just some to illustrate the stuff we handled before this. So if there's questions about this, just ask them at the end. There are specific questions from why did they use Athena, why did they use that? That's out of scope for this one. It's just an example. So I've been working with data lakes and data engineering and all those stuff for a few years now, and I've encountered some challenges or some questions that keep on coming up. And well, I've handled those together with my team, not always in a good way, but we learned from those. And I think this is a chapter I would just, these are various subjects I just want to give to you, like, okay, keep in mind, or this is a way we can handle this one. I think the biggest one is GDPR. Definitely everything data related. This has a big impact on it. I'm not a legal expert, definitely not. There is a lot in GDPR that I don't know, or I'm not proficient in. But I think three big ones for data lake design are the retention time, the right to be informed, and right to be forgotten. So your retention time basically is based on what your data is. You can store that data for a certain amount of time. Let's say we have information about a home address of a user. Well, there are rules in GDPR that define that, well, if you have that kind of data, that data you can keep for 6 months, and then it has to be gone. So yeah, this might be a challenge especially if you have a lot of files on a file system and not in incredible stores. And also if you have a big data lake, where is all the data? Now, how can we handle this? To know what type of data we have. So if we have an address, or we have a name, or if we have a phone number, or whatever, or even an image of a user. We said that a Puddle, especially an accepted Puddle, has a schema, and you can add that to that schema, where you can define, okay, this field is a string, it's a street name, and you can tag that as a GDPR field, and this is a GDPR like location of residence, or a bigger, higher order of type of GDPR data. And let's say we have a few of those fields in our Puddle there, and then it's pretty easy to just, based on the schema of that Puddle that you can expose in like a meta store or something like that, to determine how long we can keep the data, because we can just take the lowest value that we have. Let's say we have a few fields we can keep 6 months, but there's one field that's very, very delicate, and we can only keep it for 1 month. That means that this Puddle can only contain data of the last month. Now we know what the data is and how long we can keep it. Because we partition our data on the files, we also know from when that data is. So it's very easy to just remove an entire section of data based on this partitioning. Even if you use like a data store or a database, you can still keep those partitioning as columns, and you can define queries on those, especially when you have a query layer that goes above the store. So let's say we have a Presto, there we can do SQL queries on data that's on a file system via Hive, for example. We can also query data that's on Kafka even. We can query data that's in a data store. So if you keep that same partition there, it's very easy to determine what data you have of what Puddle from what time. So now we already know what data we need to remove. And now it's important that we know where the data is. Here we come back to the first things I said, that you want a single truth of data. So you know, well, my user data, my transactional user data is stored on Hadoop file system, and it's right there. And so you're certain that if there's some request that you have to remove this data, that there's only one point where you have to do this. And this solves the three problems that we have based on retention time. You can easily script this to just check every day to go over the Puddles, to just see, okay, I have these Puddles have these partitions. These Puddles can only contain data from a certain amount of time. Do we have partitions that are that are not that are older than the time that we can keep it? Then we can do a delete statement. A second one is right to be informed. So this means that a user a client or whatever could ask your company, what data do you have about me? And you should be able to respond on it. I think, I don't know what the time is nowadays. I think it's 2 weeks or something. Because our accepted data is all queryable, because we apply a schema to it and we made sure that it's queryable via a query layer, or if it's a store, well, it's just easy queryable like that. We can just define queries for each puddle that will fetch the data for a certain customer or a list of customers. That way, we already have a way to handle this right to be informed, because everything is queryable. Now, the most tricky one is the right to be forgotten. So that user could also ask you, I want you to delete all the data you have about me. Well, all the data. Sometimes you have a case that you can keep the data, especially if you're like a bank, you can't remove banking information like that, but just in general, it can ask to remove some data. If you have data stores with delete functionality, it's pretty easy. Just define some delete queries on that store for user on a user level. But if you have data on file systems and you're not using something like a Delta Lake, and it's not that easy to remove data from it. And even, I would even say, even if you're able to do deletes, I think there's a better way to keep the value of the data, but still complying to this. So that's basically working with pseudonymization. So basically, when we have data, well, you can do this before it enters your data lake environment, or you can do it in the step between the raw and accepted. But there you're going to define fields that could be traced back to a certain user. So this will be IDs, this will be names, this will be anything that the DPO or whoever is responsible to defining these rules. If it's possible to trace it back to one single person, real life person, we will create a key for it. So just we can generate a new ID, and we keep the mapping of those in the table. So there we have Thomas Bombaker is user 1 in our data lake. If we ever export this data, we can still make the translation back to the original value because we still have that mapping. If I say, well, I want you to remove my data, if we just remove the mapping, so just Thomas Bombaker is user 1, the only thing we have on our platform is user 1. And there is no way to trace it back to me as a user, Thomas Bombaker. But we still keep, we still have that data available. So it's still, if you're doing like machine learning, you want to train models on it, it's still data that's valuable because it's still, you can still make references to it. So it's still, it's not like a random anonymized user. It is still, it's a user, and he did those things, he bought those things, and he had this this kind of product at this point in time. But we can never relate it back to a certain person. So that's why we can use pseudonymization to comply to the rule to the right to be forgotten, but also not removing, still keeping the valuable data for certain cases.
But this is not the actual right to be forgotten purpose, because the right to be forgotten is meaning that you are not allowed to even use the data for any other use, even though it's anonymized. You are not allowed to do it. Even the data, you are not allowed to make some kind
again,
of.
I'm not a legal expert, but we have discussed this with multiple DPOs from multiple companies, and they all said that it was valid and it was okay, because the point of it is that it's you don't want as a person, you asking them, and I don't want you to have data about me. They don't have data about you. They have data about a user that was you, but they could never trace you back. So they don't have information on you. Now, if it's for a company that says, well, this is not sufficient for us, then okay, then you have to find different approaches. But this is a widely used strategy to handle this. And well, again, I'm not a legal expert, but this is a solution approved by multiple people who are. So if they're not telling the truth, maybe, but I can only tell you what they told me. Because it's the same, well, let's say you have data where you train a certain model. Let's say we have a recommendation system based on data, and you ask, well, I want you to remove my data, and we use that data from that user to train that model. We don't have to throw away that model or retrain that model, because yes, the information is there in a black box, but it's not traceable to a certain person. And that's the key point here, that you cannot trace it.
That's a different story. That's a different story, because the model is basically aggregation, or like a decision tree or something like that. So it's very generalized. That's allowed to keep, but you cannot keep the record, even though it's anonymized. Well, I think lately I've seen like lots of ECJ ruling around it, and they are not. There is actually someone in Denmark that is always suing, you know, and I don't think that's like you know, this approach would work. But you know, but in a legal term, not technical.
Mm-hmm.
You know, that's my take. Like, as you said, it's a legal issue.
Yeah, I know. Yeah, that's why I don't want to start a legal discussion here, because it could be that you're absolutely right. We're still in like the gray zone of GDPR, so maybe this is a solution that's on paper not 100% approved, but it might be okay for now. I don't know. This is just the technical solution I came up with the input I got from the people specialized in it. So it could be that you're right, but yeah, I mean, I can't argue legal stuff about this, because I don't know. But I know from a technical point of view, and the implementation of this is widely used and accepted by multiple people. So yeah, if they're all wrong, maybe it could be, but I'm pretty interested in it. If you would like to discuss this further, but maybe after this or via mail or something. But I would love to hear more about your take on it, and why it's not.
Yeah, like the main. Well, in the discussion I had with the client, they said it was in.
So yeah, definitely hit me up with an email, and then we'll definitely
sure
discuss this further, because it's a really complex. It's a complex topic, and I think there are a lot of people searching for the perfect solution, and if there are problems with this one, I would love to hear it from you. But for now, let's keep going. We have some schema evolution. Well, the data we are ingesting from our sources are not always going to be the same schema. Let's say some fields are added, some fields are becoming optional or not. Most of the stores and processing tools can handle non-breaking changes, like an extra field or something. There are some weird stuff, especially in Spark, how he handles the determination of what the actual schema is. That's why I think if you have a lot of those schema changes, that you don't rely on the implicit schema definition Spark makes, or any other tool, but just explicitly create a schema. If you have breaking changes, this means that you have a new puddle, because if you can't be sure that all the data in a single puddle can be read with one schema, you have to create a separate one, because that's breaking our core rule of a puddle, that it has one schema and one type of data. But yeah, I think if you're using Kafka, especially in combination with Avro and the schema registry from Confluent, these are things that already are that work out of the box there. Again, Spark also is pretty okay with handling it. But keep in mind, if you have breaking changes, don't try to append it, and like say, okay, if you read it from this point in time until this point in time, you can use this schema. If you use it from this point in time, use this schema. This is that's not a great way of working. This is for file systems. If you have a lot of small files, most of the time it's a big issue. Also a lot of partitions. That's why I said if you're going to go for like an every 15 minutes adding new partitions, there is a limit in Hive, for example, how many partitions it can handle, and also the files for your file system. Big data tools work better with bigger files than a lot of small files. There are something you can do about small files. You can have a process that just compacts the files, just reads in all the small files, writes it back as one big file. And for partitioning, you can still have a data source that runs every 15 minutes or every half an hour, but you can store it on, let's say, a daily partitioning level. This means that on your file system, you'll see a structure up until your day, but in your data itself, you will have an hour column, for example. The way you can do this is if you're reading new data, you actually need to, if you're writing new data, you have to read in all the data you've already written for this day and append this data and write it back. This might cause some issues, especially when you're using Spark, because it's not atomic, and Spark itself is pretty lazy to reading files and data that you're using, and it will keep on expecting that it's a certain file name, but the data is, if it's not anymore that specific file name, it will complain about the files missing. So this is an easy one to say as a strategy, but it's harder to implement. If you're using something like Datalake, this helps a lot with this. But just keep in mind, try to avoid small files in a file system and a lot of partitions if it doesn't make sense in your Hive. Then data quality is a big one. So in every stream, between every puddle, we can keep some basic metrics based on, well, we have that many records that made it into a raw puddle on a certain day, and like 90% of that made it until the accepted folder. So that might be acceptable. But if you see that one day that only 10% of it made it into the accepted folder, then that's an issue that you might check out. So that data will be in raw available, but not in accepted. You can add an extra type of puddle that we call the rejected puddle to move when you do this step from raw to accepted. You can let all the good records flow into the accepted record, and the bad records you can put into the rejected puddle. So it's easier to get those malformed records and to figure out what's wrong with them. So yeah, you can monitor these metrics, as I said. Yeah, you can do it manually by just checking it, but you can also define some rules or some algorithm that will decide what seems like an outlier, seems like a weird metric that we get. And yeah, normalization, I already talked about this for data quality. Make sure that all your dates are in the same date format if it's possible, and just have a general rule of how certain type of fields are represented in your data. And then another one, right tool for the job. Just because you're very proficient in NiFi and Python doesn't mean you always have to use these tools. It might be an argument to use them if you have a lot of knowledge in your team to use a certain data store. And well, technically another one would be very optimal, but the other one is sufficient. Well, just use the one that you're already proficient in as a team, so you don't have to learn like 10 different topics. So that's a balancing that you need to do between those two. One thing also is don't use big data tools if it's not needed. If it's small data, don't use a Spark job for it. The only argument I would make to use Spark for everything is if you're creating some sort of framework or like helper functions that for example, make an abstraction of loading in data, of writing in data in Spark, of like applying a schema to it. If you already have those, well, yeah, just keep using Spark, because if you have to develop it in other languages or other technologies, it might, yeah, it's not worth the change of tool. Okay, so we're coming at the end of the presentation. If there are any like general questions about it, this is a great time to do it. If not, the next slide will be my contact details. If it's like a very specific question about a specific use case, for example, just send me an email. I'm not promising I will answer it right away, but it will be on my to-do list. I love to hear other stories from other clients, I think, or like other approaches to handling this kind of stuff. I think it's this type of knowledge sharing that these webinars also provide a platform for me. It's very interesting for everyone. Yeah. So if are there any more questions?
I think not Thomas. Actually, in chat, most people are leaving because we are running a bit behind schedule. We're 20 minutes over the hour mark, so a lot of people.
Okay, sorry, I got too excited. I lost.
It's okay, but if people that are still here, because a few people are skipping out, still have questions, definitely ask them. But majority left due to most likely back to work.
Yeah, they probably have other meetings coming up.
Yeah, exactly.
I do too, so I still have time, but not another half an hour right now.
No. Yeah.
Okay, so from the ones that are still here, any questions, remarks, criticisms? No? Okay. I would definitely, for the GDPR one, definitely send me an email after this one. I would really like to, discuss it further, because it's, it's pretty important, that one. Okay, then I think I want to thank you all. I mean, the ones that are still here, for listening to me.
Yeah, they are all positive. I mean, if they are positive, so.
Okay, I wish you all a good health and a good rest of the week.